Module 31, Lecture B, Parallel Configuration. By the end of this lecture, you will be able to configure Scikit-Learn Parallelism using njobs and joblib-aware estimators, manage thread pools and avoid oversubscription in nested parallel workloads, and benchmark and cache workflows to improve repeatable performance. Parallel Basics. Joblib Parallelism. Joblib provides Scikit-Learn's main way to run independent machine learning tasks in parallel across multiple CPU cores. It is especially useful for work like cross-validation and grid search, where many tasks can be handled separately. Scikit-Learn estimators use joblib to manage scheduling and collect results, giving users a consistent interface while the library handles the parallel execution. Joblib Parallelism lets Scikit-Learn split independent work across multiple workers, which can make tasks run faster when coordination is efficient. This is useful for models such as ensembles, where separate parts can be trained independently and then combined. Joblib handles distributing the work and collecting the results for Scikit-Learn. Joblib Parallelism is not always faster, because starting workers and coordinating tasks adds overhead. For small data or quick operations, this cost can cancel out any speedup. It works best for many independent, expensive tasks, such as repeated model fitting or building ensemble trees. Even with estimators that support joblib, you should consider task size, CPU cores, and other parallel work already running. Python code Joblib Parallelism. This script shows how Scikit-Learn uses joblib for parallel processing. It compares cross-validation runs with different numbers of parallel jobs and highlights that parallelism can add overhead, so more jobs do not always mean faster results. We import NumPy for numerical work and use Scikit-Learn for machine learning tools. From Scikit-Learn, we use a dataset generator for classification, a random forest classifier for building the model, and cross-validation scoring to evaluate how well the model generalizes to new data. We create a reproducible classification dataset using Scikit-Learn's make classification function. It contains 1,200 samples with 20 features, including 12 informative features that help determine the target. Setting the random state to 42 ensures the same data is generated each time, making model testing and comparison consistent. Before modeling, the code verifies that the feature data has 1,200 rows and 20 columns. If the data does not match this expected structure, it raises an error. This check helps catch formatting problems early and prevents issues during model training. We create a random forest classifier for a classification task using 80 trees. A fixed random state makes the results reproducible, while using one processor core runs the model sequentially. This setup provides a baseline for comparing performance with parallel execution later. We evaluate the model using Scikit-Learn cross-validation with 3 folds. The data is split into 3 parts, and the model is trained and tested 3 times, each time using a different part for testing. Running with one job keeps the process sequential, helping assess performance in a single-threaded setup. A new random forest classifier is created with 80 trees and the same random state of 42 for reproducibility. The main change is using 2 processing jobs, allowing training to run on 2 CPU cores in parallel. This can speed up model training by sharing the workload across processors. We evaluate a random forest classifier using Scikit-Learn's cross-validation tool. The model, feature data, and target data are tested with 3 folds, so the data is split into 3 training and testing rounds. Both the model and the evaluation use 2 processing jobs, allowing work to run in parallel and potentially speed up computation. The code checks the Scikit-Learn version for reproducibility, then compares average cross-validation accuracy for the same model run with different scheduling settings. It reports the mean accuracy for a single worker and for two workers, rounded for readability. The key point is that the number of jobs setting controls how many workers are used for parallel processing. This script compares sequential and parallel cross-validation in Scikit-Learn using a synthetic classification dataset and random forest models. One model runs with a single job, while the other uses two parallel jobs, with the same settings for reproducibility. The results show that parallel processing can reduce runtime, but it does not change the model's accuracy, since it affects how the work is executed, rather than how the model learns. Setting n jobs. The number of jobs setting controls how much parallel work a Scikit-Learn estimator uses. One job runs tasks sequentially, which is useful for small tests or debugging, while higher values request more workers. Setting it to -1 uses all available CPU cores, helping speed up divisible tasks like random forests or grid searches. Choosing how many jobs to run in parallel is a balance between speed and overhead. Small tasks may slow down because creating workers and moving data takes time, while larger tasks can benefit greatly from parallel execution. On personal or shared machines, avoid using every core if it would make other applications sluggish or interfere with other users. Use n jobs deliberately because different Scikit-Learn estimators apply parallelism at different levels. Some estimators parallelize their own independent work, while tools like cross-validation parallelize across model fits. Avoid letting both inner and outer steps use many workers at once, since nested parallelism can create too many tasks. Choose one main level for parallel work, such as hyperparameter candidate fits or a large ensemble model. Python code setting n jobs. This example compares two settings for the number of parallel workers used by a random forest. Because random forests can train multiple trees at the same time, the output reports both the model accuracy and the worker setting used. We import key tools from Scikit-Learn to build and evaluate a classification model. The breast cancer dataset provides sample data, the random forest classifier trains an ensemble of decision trees, and the train test split function separates the data for training and testing. Finally, the accuracy score measures how well the model's predictions match the true labels. We load Scikit-Learn's breast cancer dataset, a standard dataset for classification tasks. The data is separated into input features and target labels, which allows the model to learn from the features and be evaluated on how well it predicts the labels. Before modeling, confirm that the feature data and target labels have the same number of rows. If they do not match, raise an error to flag the dataset inconsistency. This simple check protects data integrity and helps prevent training problems later. The dataset is divided into training and testing sets, so the model can be evaluated on unseen data. Scikit-Learn's train test split function reserves 25% of the data for testing, while stratification keeps the class balance consistent across both sets. A random state of 42 makes the split reproducible each time the code runs. We create a random forest classifier with 80 trees and limit training to one processor core, which helps compare performance under restricted computing resources. A fixed random state makes the results reproducible. The model is then trained on the feature and label data so it can learn patterns and make predictions on new data. A random forest classifier is configured to train efficiently by using all available CPU cores. It uses 80 trees and a fixed random state of 42, so results can be reproduced. The model is then trained on the feature data and labels to learn the patterns needed for classification. We compare the accuracy of two models, one trained with a single worker and one trained using all available CPU cores. In each case, the accuracy score compares the test labels with the model's predictions. This shows whether using more workers changes the model's accuracy. The code reports the Scikit-Learn version to support reproducibility, then compares model accuracy when training with one worker versus all available CPU cores. Both accuracy values are rounded for readability. The key point is that changing the number of jobs affects how computation is parallelized, not what the model is trying to learn. This script compares training a random forest classifier on the breast cancer dataset using one processor versus all available CPU cores. Both models use 80 trees and are tested for accuracy after training. The results show that using more parallel jobs can change training speed and resource use, but it does not meaningfully change the model's accuracy or learning outcome. The script also reports the Scikit-Learn version and the accuracy for each setup. Backend contexts. Backend contexts in Scikit-Learn and joblib control how parallel work is run, such as with processes or threads. Estimators that use an end-job setting often rely on joblib to schedule this work. Choosing the right backend matters because different tasks perform better with different forms of parallelism. Setting a backend context lets users apply a consistent parallel strategy across joblib-aware estimators without changing each one separately. In backend systems, parallel work is usually handled with either separate processes or threads. Processes can run truly in parallel across multiple cores, but may add overhead with large data. Threads stay within one process and can be efficient when compiled libraries manage threading well. The key is not to add more workers blindly, but to match the parallelism strategy to the workload. Backend contexts help control parallel work in Scikit-Learn workflows that use multiple joblib-aware steps, such as feature extraction and model fitting. Without this control, different parts may compete for all available cores and reduce performance. Choosing an appropriate backend lets you match parallel execution to your hardware and workflow, making runs faster, more stable, and easier to manage. Python code, backend contexts. This script shows how joblib backend contexts affect scheduling, comparing process-based and thread-based choices. The results indicate that the estimator configuration remains consistent across these backend options. This setup imports the main tools needed to build and evaluate a classification model. Scikit-Learn provides the machine learning utilities, while joblib's parallel backend helps control whether tasks run with processes or threads. The make classification function creates a synthetic dataset. The random forest classifier builds an ensemble of decision trees, and cross-validation scores measure the model's performance across repeated train test splits. We create a small synthetic classification dataset with Scikit-Learn's make classification function. It includes 800 samples with 12 features, 8 of which help determine the target. A fixed random state makes the data reproducible, giving us a controlled and efficient setup for testing the model. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that each example has a matching label. If they do not align, it stops with an error to prevent training on inconsistent data. This setup creates a Scikit-Learn random forest classifier using 40 decision trees. It uses 2 CPU cores to speed up training, which can help with larger datasets, and sets the random seed to 42 so the results are reproducible. The backend is set to loky, joblib's default process-based option, so parallel work runs in separate processes. Within this setup, a random forest model is evaluated with threefold cross-validation using 2 parallel jobs. The resulting cross-validation scores are stored for later use. This section uses joblib's parallel backend with threading, so tasks run with threads instead of separate processes. Within that setup, Cross-validation evaluates the random forest model on the feature and target data using 3 folds and 2 parallel jobs. This lets us compare the threading approach with the earlier process-based parallel execution. We compute the average cross-validation score for both the process-based and thread-based backends, convert each result to a standard number, and round it to 3 decimal places. This makes the 2 scores easy to compare and presents the performance difference in a clear, concise way. The output checks the Scikit-Learn version for compatibility, shows how many parallel jobs the random forest classifier uses, and compares mean accuracy under process-based and thread-based scheduling. These results show how the same model performs with different parallel backends. Changing the backend affects only how tasks are scheduled, not the model's goal or configuration. This script compares process-based and thread-based parallel scheduling with joblib while training the same random forest classifier. It uses a synthetic dataset, 2 parallel jobs, and 3-fold cross-validation for both backends. The output reports the Scikit-Learn version, the estimator's job setting, and the mean accuracy for each backend. The key point is that changing the backend affects how work is scheduled, but not the model's purpose or configuration. Thread pool control. OpenMP awareness. OpenMP lets compiled numerical and machine learning libraries run work across multiple CPU threads, even when a Python program appears to perform one task. This can speed up large operations, but it becomes harder to manage when combined with higher-level parallel tools like joblib. In Scikit-Learn workflows, Python may coordinate the experiment, joblib may distribute tasks, and OpenMP may accelerate the underlying computations, so performance control requires awareness of all these layers. OpenMP controls how many threads a routine can use for parallel work, such as in clustering or tree-based algorithms. Using all available cores for one task can be efficient, but running many tasks at once with the same thread count can overload the system. This oversubscription causes excessive thread switching and resource contention, which can reduce performance. Managing OpenMP settings is especially important in nested or simultaneous workloads. Manage OpenMP by choosing how to allocate CPU cores across your work. The best thread setting depends on data size, task cost, available cores, and other running processes, so more threads do not always mean faster results. By recognizing when OpenMP is active and measuring performance realistically, you can avoid oversubscription and make workflows more stable and efficient. BLAS thread pools. In scientific Python, optimized numerical libraries such as BLAS often run their own threads behind the scenes. They can spread heavy linear algebra work, like large matrix multiplication, across multiple CPU cores, even when the Python code itself is not written in parallel. This hidden threading can provide major speedups for workloads that rely on large matrix operations. BLAS thread pools can interfere with higher-level parallelism in machine learning. If several parallel tasks each call numerical routines that start their own threads, the total number of threads can exceed the available CPU cores. This oversubscription often slows performance because threads compete for resources, switch too often, and use caches inefficiently. The problem is common in nested workloads where both the machine learning framework and the numerical library manage parallelism. Manage BLAS thread pools by choosing where parallelism should occur and limiting competing layers. For many independent tasks, keep each BLAS call to only a few threads so the outer scheduler can use CPU cores predictably. For workloads dominated by large numerical operations, allowing BLAS to use more threads may be faster. Monitor runtime and system responsiveness to keep thread pools efficient, stable, and well-balanced. Python code, BLAS thread pools. This example compares choices for BLAS thread pools during matrix multiplication. Because these operations often use native worker threads, using too many threads at once can oversubscribe the CPU. The timings show that oversubscription may waste cores and reduce efficiency. We import NumPy to handle arrays and perform efficient numerical computations in Python. We also import joblib's parallel backend tool to manage parallel execution, including how many threads are used. This helps improve performance for demanding operations, such as matrix multiplication. We create a NumPy random number generator with a fixed seed of 42. This makes the random values repeatable each time the code runs, which helps ensure consistent results for debugging and performance comparisons. We create two 900 by 900 matrices using NumPy's random number generator with normally distributed values. The matrices are kept at this size, so the computation remains manageable and runs quickly in environments such as Google Colab. Before multiplying two matrices, the code verifies that the left matrix has the same number of columns as the right matrix has rows. If the shapes are incompatible, it raises a value error instead of attempting the operation. This check helps prevent multiplication from failing at runtime. The function measures the time needed to multiply two matrices while controlling the number of threads used by the underlying linear algebra library. It records the start time, runs the multiplication inside a parallel backend with a specified thread limit, then records the end time. It returns the elapsed time in milliseconds and the first value of the result matrix, which provides a simple check that the computation ran correctly. We run the matrix multiplication function twice, first with one thread and then with two threads. Each run records the execution time and the first value in the resulting matrix. Comparing these results shows how changing the number of threads affects performance. The code checks whether matrix multiplication gives the same result with one thread and two threads. It takes the absolute difference between the two outputs and uses that value as a checksum. A zero or negligible difference confirms that both threading settings produce matching results. The script compares matrix multiplication performance when BLAS uses one thread versus two threads under Scikit-Learn's parallel backend. It reports both timings and the numerical difference between the results. The key lesson is that in nested parallel jobs, limiting inner BLAS threads helps avoid CPU oversubscription and inefficient performance. This script shows why controlling BLAS thread pools matters during matrix multiplication. It multiplies two random 900 by 900 matrices while limiting BLAS to one thread and then two threads, using joblib to enforce the setting. The timings show that more threads are not always faster, especially when nested parallel work causes oversubscription. Both runs produce the same result, so the key lesson is to manage thread usage carefully to use CPU resources efficiently. Avoiding oversubscription. Avoiding oversubscription means keeping the number of active threads or processes within what the computer can handle efficiently. In parallel machine learning, this can happen when one parallel task starts other threaded work, creating too many threads overall. The result is often slower performance due to excessive thread switching, memory bandwidth congestion, and poorer cache use. Treat processor cores as a shared resource and match parallelism to the workload. If tasks already run across multiple processes, limit the threads used inside numerical libraries, often to one per process. If the main work is a large linear algebra operation, let libraries such as BLAS or OpenMP use more cores and keep outer parallelism low. In short, small tasks usually benefit from job-level parallelism, while large numerical tasks benefit from internal parallelism. In shared or production systems, oversubscription wastes threads and can slow down other jobs or services. A program may use more threads than the cores it requested, causing interference, latency spikes, sluggish notebooks, or unreliable benchmarks. To avoid this, choose which layer should use the available cores, limit the others, and confirm performance with realistic timing tests. Python code. Avoiding oversubscription. This example shows how to budget threads in nested parallel work. It highlights that oversubscription occurs when each layer tries to use all available cores and compares risky thread choices with safer ones. We import NumPy for numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use a dataset generator, a random forest classifier, and cross-validation scoring. Together, these tools let us create synthetic classification data, train an ensemble model, and evaluate its accuracy. We create a reproducible classification dataset using Scikit-Learn's make classification function. It generates 1,200 samples with 12 features, using a fixed random state of 42. The result includes the input features and the target labels for each sample. The code first verifies that the feature data has the expected size, 1,200 rows and 12 columns. If it does not, it raises an error to signal that the data format is not correct for the lesson. This early check helps prevent modeling problems caused by incorrectly structured data. The code models a notebook with 4 available CPU cores and sets the outer processing layer to run 4 jobs in parallel. It also gives each job 4 threads, which is risky because all 4 jobs may try to use all 4 cores at the same time. Without careful management, this can cause oversubscription. The risky plan uses 4 outer jobs and 4 inner threads, creating 16 workers and risking oversubscription. The safer plan keeps the 4 outer jobs, but limits each inner job to 1 thread, so only 4 workers run and oversubscription is avoided. We configure a Scikit-Learn random forest classifier with 40 decision trees. Each tree is limited to 1 job to avoid excessive parallelism, and a fixed random state makes the results reproducible across runs. The code uses Scikit-Learn cross-validation to evaluate a random forest classifier on the given features and target. It splits the data into 4 folds and runs the outer cross-validation in parallel using 4 jobs, helping use multiple cores efficiently without overloading the system. The output checks the Scikit-Learn version and available CPU cores to support reproducible, resource-aware processing. It compares a risky nested parallel plan, where outer jobs and inner threads can create too many workers, with a safer plan that limits each outer job to 1 thread. Finally, it reports the mean cross-validation accuracy from the safer plan, rounded to 3 decimal places to evaluate performance under controlled parallelism. This script shows how to avoid oversubscription when using nested parallel tasks. With 4 CPU cores available, it keeps each random forest estimator single-threaded and lets cross-validation use the 4 parallel jobs. It compares a risky plan, where both inner and outer work use all cores, with a safer plan that parallelizes only the outer layer. The main lesson is that matching parallel work to the core budget helps maintain performance while still producing the cross-validation accuracy. Configuration benchmarking. Global performance switches. Global performance switches set how a machine learning workflow uses computing resources before any model tuning begins. They control things like worker counts, numerical library threads, reuse of intermediate results, and diagnostic output. Standardizing these settings makes performance more intentional, repeatable, and comparable across environments, instead of depending on hidden system defaults. Global performance settings in Python help coordinate data loading, pre-processing, and model fitting, so they do not compete for the same resources. Without them, libraries may overload the same cores, causing slowdowns that hide the true performance of a workflow. Setting these controls creates a more predictable environment and makes benchmarking results easier to trust. Treat global performance switches as part of your experimental setup, just like model or dataset settings. For benchmarking, focus on consistent results rather than a single fastest run, and choose settings that match the environment, from cautious personal use to more aggressive server use. Documenting and standardizing these choices makes results clearer, more reproducible, and easier to compare fairly. Python code. Global performance switches. Benchmarking depends on stable global performance settings. This example compares caching and worker choices, showing that they can produce consistent timing differences. We import NumPy for numerical computing and Scikit-Learn for machine learning tools. From Scikit-Learn, we use tools to create a synthetic classification dataset, reduce dimensions with principal component analysis, train a logistic regression classifier, evaluate it with cross-validation, and combine these steps into one workflow using a pipeline. To make the benchmark comparison fair, we create one fixed, reproducible dataset using Scikit-Learn's classification data generator. The dataset has 1,200 samples with 20 features, including 12 informative features that help determine the target. A random state of 42 keeps the data consistent across runs. Before benchmarking, the code verifies that the feature data has 1,200 rows and 20 columns. This ensures the dataset matches the expected structure and keeps training and evaluation consistent. If the dimensions are wrong, it raises an error early to prevent later problems. We build a Scikit-Learn machine learning pipeline with 2 steps. Principal component analysis to reduce the data to 8 components, followed by logistic regression for classification. Random states are set for reproducibility, and logistic regression is allowed up to 300 iterations. This pipeline is then used to process the data and compare performance under different settings. We evaluate the model using 5-fold cross-validation, where the data is split into 5 parts, and each part is used once for validation. The cross-validation uses the model, feature data, and target data running on a single processor core. This gives a baseline measure of performance for comparison with other settings. The code uses Scikit-Learn cross-validation to evaluate a pipeline that combines principal component analysis with logistic regression. It runs 5-fold cross-validation on the feature and target data, using 2 processing cores in parallel. This can make evaluation faster, but the number of workers should be chosen carefully to balance speed with available resources. The benchmark records the Scikit-Learn version for reproducibility, then compares the same dataset and model using 5-fold cross-validation. It reports the mean accuracy for runs with 1 worker and 2 workers, rounded for readability. The key lesson is that the number of jobs should be documented when comparing timing results, because global settings can strongly affect performance. This script benchmarks a machine learning pipeline with different numbers of workers. It uses a synthetic dataset, combines principal component analysis with logistic regression, and compares cross-validation results using 1 worker versus 2. The main lesson is that worker settings can affect timing and results, so the number of jobs should always be recorded to make benchmarks consistent and repeatable. Workflow caching. Workflow caching improves efficiency by saving the results of expensive steps so they do not need to run again. In machine learning, this lets unchanged tasks like data loading or feature extraction be reused while researchers adjust models. As a result, experiments can resume from cached points and focus resources only on what has changed. In Scikit-Learn, caching is commonly used with pipelines to save the results of expensive pre-processing steps, so they can be reused instead of recomputed. This can speed up workflows where transformations, such as feature extraction from text or images, take most of the time. However, caching adds overhead, so it may not help when computations are fast or the data changes often. Always check whether caching actually improves performance for your specific workflow. Workflow caching can save time, but it uses storage and can affect reproducibility. Large cached outputs may consume significant disk space, so teams need to monitor cache size. Performance comparisons should also state whether the cache was cold or warm, because later runs may appear faster when previous results are reused. In practice, caching is useful for development and retraining, but benchmarks should clearly document any cached computations. Python code. Workflow caching. This script shows how workflow caching can make pipeline benchmarks faster. By reusing cached preprocessing results, repeated runs take less time. The output highlights the timing difference between a cold cache and a warm cache. We import NumPy and key tools from Scikit-Learn to build a machine learning workflow. These tools let us create a synthetic classification dataset, split it into training and testing data, standardize the features, reduce dimensionality with principal component analysis, train a logistic regression model, and measure prediction accuracy. Together, they provide the components needed for a complete pipeline with caching support. We create a synthetic classification dataset using Scikit-Learn's make classification function. It generates 1,200 samples with 20 features, 10 of which are informative for predicting the class labels. A fixed random state of 42 makes the data reproducible, and the function returns the generated feature data along with the target labels. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 1/4 reserved for testing. Stratification keeps the target distribution similar in both sets, and a fixed random state makes the split reproducible each time the code runs. Before benchmarking, the code verifies that the training and test datasets have the same number of features. This confirms they are compatible for processing. If the counts differ, it raises an error, so the data preparation issue can be fixed first. We build a machine learning pipeline that combines preprocessing and modeling in one organized workflow. The data is first standardized with standard scalar, then reduced to 8 principal components using PCA for dimensionality reduction. A logistic regression model is then applied, with settings chosen to support consistent results across runs. This makes the full process more efficient, reproducible, and easier to manage. We can simulate reusable workflow results with a small in-memory cache that stores pre-processing outputs. This lets future runs reuse those results instead of recalculating them, which can speed up machine learning pipelines. With pre-processing cached, we can focus on changing other settings, such as model strength, without repeating the full workflow. The function uses a cache key to avoid repeating pre-processing when the same training data shape and PCA setting have already been processed. If needed, it scales the training features, applies PCA to reduce their dimensions, and stores the results. Otherwise, it reuses the cache data. It then trains a logistic regression model on the reduced training data, applies the same scaling and PCA steps to the test features, makes predictions, and returns the accuracy against the true test labels. Benchmarking begins by clearing the cache, so earlier data cannot affect the results. The model is then fit with a strength of 1.0, while pre-processing results are stored for faster future runs. This first fit is the cold run, so its accuracy is recorded before any cache benefit, and the cache size is checked to see how much pre-processing was saved. We run the model a second time using the cached pre-processing results, but change the regularization strength to 0.5. This lets us compare performance under a different setting without repeating pre-processing. Afterward, we check the cache size to confirm it stayed the same, showing that the cache steps were reused. The output first reports the Scikit-Learn version to support compatibility and reproducibility. It then compares the number of cached pre-processing entries after a cold run and a warm run, showing that the second run reused stored pre-processing work. Finally, it prints the rounded accuracy for both runs, demonstrating that caching improves workflow efficiency while only the model parameters change. This script shows how caching can make repeated machine learning pipeline runs more efficient in Scikit-Learn. It builds a classification pipeline with scaling, principal component analysis, and logistic regression. Then compares a first cold run with a later warm run. The warm run reuses cached preprocessing results and only refits the classifier with a different regularization setting, avoiding redundant work. The output reports the Scikit-Learn version, cache usage, and accuracy, showing faster reuse of preprocessing while keeping similar model performance. Performance benchmarking. Performance benchmarking measures how workflows actually run under real conditions. In parallel machine learning, adding more workers can improve speed, but it can also slow things down because of coordination and data movement. A useful benchmark looks at runtime along with factors such as dataset size, feature count, and the number of parallel jobs, helping teams choose systems based on evidence rather than assumptions. When benchmarking, separate one-time setup costs from ongoing computation. Loading data or transforming features may be expensive at first, while later runs can be faster because cached intermediate results are reused. Always state whether the benchmark is a cold run with no cache or a warm run with preloaded data. Caching can speed up experiments, but the initial preprocessing cost still matters for realistic deployment planning. Reliable benchmarking requires running tests multiple times and interpreting results carefully because single measurements can be distorted by background activity or delays. Benchmarks should reflect real-world workloads and environments, not just small samples or personal machines. The goal is to choose a stable setup that balances speed, resource use, and reliability, helping teams make better decisions about parallel settings, hardware, reproducibility, and scalability. Python code performance benchmarking. Benchmarking measures repeated workflow runtimes, while caching separates one-time setup from computations that can be reused. The results distinguish cold timings from warm timings, showing performance before and after cached work is available. We import the temp file module to create temporary files and directories for caching benchmark data without changing the permanent file system. We also import the performance counter from the time module, which provides a high-resolution timer for accurately measuring how long code takes to run. This setup imports the main tools needed for a classification benchmarking script. It uses NumPy for numerical work, matplotlib for plotting, and Scikit-Learn to create a synthetic classification dataset, reduce its dimensions with principal component analysis, train a logistic regression model, and evaluate it with cross-validation. A pipeline is included to combine preprocessing and modeling steps, and the Scikit-Learn version is recorded for reproducibility. For fair benchmarking, we create one fixed classification dataset using Scikit-Learn. It has 2,500 samples with 20 features, including 12 informative features that help determine the target. A fixed random seed of 42 makes the dataset reproducible, so different benchmark runs can be compared consistently. The code first verifies that the feature data has 2,500 rows and 20 features. If the dimensions are wrong, it raises an error instead of continuing. This check helps ensure the dataset is properly structured before benchmarking begins. This pipeline reruns principal component analysis each time the benchmark is executed. It first reduces the data to 10 components, then trains a logistic regression model with a fixed random state and up to 300 iterations. Because no caching is used, every run starts from scratch and recomputes the PCA transformation before evaluating the model. The function measures both model performance and runtime. It starts a high-resolution timer, runs threefold cross-validation on the estimator using the feature and target data on one processor core, then calculates how much time passed. It returns the cross-validation scores along with the elapsed time, so you can compare the estimator's accuracy and speed. A temporary directory is used to cache intermediate results in a scikit-learn pipeline. The pipeline first applies principal component analysis to reduce the data to 10 components, then fits a logistic regression model with fixed settings for reproducibility. By enabling caching, the PCA results can be reused on later runs, making warm runs faster. First, we run cross-validation on the basic pipeline without caching. A timing function records both the cross-validation scores and how long the run takes. This gives us a baseline for comparing the effect of caching later. The cached pipeline is evaluated with cross-validation for the first time, so no stored results are available yet. A timed cross-validation scoring function returns both the performance scores and the total runtime. These results represent the cold run, which provides a baseline for comparing later runs that can use cached data. Next, we run the cached pipeline a second time. Because earlier transformations can be reused, this is a warm run. We measure the cross-validation scores and the time taken for this cached run. The code sets up labels for 3 benchmark workflow configurations: plain, cached cold, and cached warm. It then stores the mean cross-validation accuracy for each configuration by averaging their score results. This makes it easy to compare the workflows based on accuracy. The output reports the scikit-learn version, then compares accuracy and runtime for a plain pipeline and a cached pipeline. It shows mean cross-validation accuracy for the plain run, the cached cold run, and the cached warm run, all rounded for readability. It also reports the runtime for each case, highlighting that the first cached run may take longer, while the warm cached run should be faster because cached results can be reused. This code creates a compact bar chart comparing mean cross-validation accuracy across 3 workflow configurations: plain, cached cold run, and cached warm run. It uses different colors for each bar, adds clear axis labels and a descriptive title, and limits the vertical scale to the relevant accuracy range from 0.7 to 1. The plot is then displayed to make the benchmark results easy to compare visually. This script compares a scikit-learn machine learning pipeline with and without caching. It uses a synthetic classification dataset and measures cross-validation accuracy and runtime for a plain run, a first cached run, and a second cached run. The plain and first cached runs take about the same time, but the second cached run is much faster because it reuses the PCA transformation. Accuracy stays consistent, showing that caching improves speed without changing model performance. In this lecture, you learn to configure scikit-learn parallelism using njobs and joblib-aware estimators, manage thread pools, and avoid oversubscription in nested parallel workloads, and benchmark and cache workflows to improve repeatable performance. In the next module, Module 32, we will go over production persistence.
Thank you for your attention. See you all in the next lecture.